Sylvanus Thompson. Elementary Lessons in Electricity and Magnetism. 1895. All books on my channel are in public domain. For more content like this, subscribe, like, and comment. Lesson 3. Electrification by influence. 22. Influence. We have now learned how two charged bodies may apparently attract or repel one another. It is sometimes said that it is the charges in the bodies which attract or repel one another. But as electrification is not known to exist except in or on material bodies, the proof that it is the charges themselves which are acted upon is only indirect. Nevertheless, there are certain matters which support this view, one of these being the electric influence exerted by an electrified body upon one not electrified. Suppose we electrify positively a ball C, shown in figure 17, and hold it near to a body that has not been electrified. What will occur? We take for this experiment the apparatus shown on the right, consisting of a long sausage-shaped piece of metal, either hollow or solid, held upon a glass support. This conductor, so called because it is made of metal which permits electricity to pass freely through it or over its surface, is supported on glass to prevent the escape of electricity to the earth, glass being a non-conductor. The influence of the positive charge of the ball placed near this conductor is found to induce electrification on the conductor, which, although it has not been rubbed itself, will be found to behave at its two ends as an electrified body. The ends of the conductor will attract little bits of paper, and if pith balls be hung to the ends they are found to be repelled. It will, however, be found that the middle region of the long-shaped conductor will give no sign of any electrification. Further examination will show that the two electrifications on the ends of the conductor are of opposite kinds, that nearest the excited glass ball being a negative charge, and that at the farthest end being an equal charge, but of positive sign. It appears then that a positive charge attracts negative and repels positive, and that this influence can be exerted at a distance from a body. If we had begun with a charge of negative electrification upon a stick of sealing wax, the presence of the negative charge near the conductor would have induced a positive charge on the near end, and negative on the far end. This action, discovered in 1753 by John Canton, is spoken of as influence or electrostatic induction. It will take place across a considerable distance. Even if a large sheet of glass be placed between, the same effect will be produced. When the electrified body is removed, both the charges disappear and leave no trace behind, and the glass ball is found to be just as much electrified as before. It has parted with none of its own charge. It will be remembered that on one theory a body charged positively is regarded as having more electricity than the things round it, while one with a negative charge is regarded as having less. According to this view, it would appear that when a body, such as the plus electrified glass ball, having more electricity than things around it is placed near an insulated conductor, the uniform distribution of electricity in that conductor is disturbed, the electricity flowing away from that end which is near the plus body, leaving less than usual at that end, and producing more than usual at the other end. This view of things will account for the disappearance of all signs of electrification when the electrified body is removed, for then the conductor returns to its former condition, and being neither more nor less electrified than all the objects around on the surface of the earth, will show neither positive nor negative charge. The action is not, however, a mere action at a distance. It is one in which the intervening medium takes an essential part. Consider figure 18. What takes place when an insulated, non-electrified metal ball B is brought under the influence of a positively electrified body A? At once some of the electric lines of the field that surrounds a pass through B, entering it at the side nearer A, and leaving it at the farther side. As the ball B has no charge of its own, as many electric lines will enter on one side as leave on the other. Or, in other words, the induced negative charge on one side and the induced positive charge on the other will be exactly equal in amount. They will not, however, be quite equally distributed, the negative charge on the side nearer A being more concentrated, and the lines in the field on that side denser. 23. Effects of influence. If the conductor be made in two parts, which while under the influence of the electrified body are separated, then on the removal of the electrified body the two charges can no longer return to neutralize one another, but remain each on its own portion of the conductor. If the conductor be not insulated on glass supports, but placed in contact with the ground, that end only which is nearest the electrified body will be found to be electrified. The repelled charge is indeed repelled as far as possible into the walls of the room, or, if the experiment be performed in the open air, into the earth. One kind of electrification only is under these circumstances to be found, namely, the opposite kind to that of the excited body, whichever this may be. The same effect occurs in this case as if an electrified body had the power of attracting up the opposite kind of charge out of the earth. The quantity of the two charges thus separated by influence on such a conductor in the presence of a charge of electricity depends upon the amount of the charge, and upon the distance of the charged body from the conductor. A highly electrified glass rod will exert a greater influence than a less highly electrified one, and it produces a greater effect as it is brought nearer and nearer. The utmost it can do will be to induce on the near end a negative charge equal in amount to its own positive charge, and a similar amount of positive electrification at the far end. But usually, before the electrified body can be brought so near as to do this, something else occurs which entirely alters the condition of things. As the electrified body is brought nearer and nearer, the charges of opposite sign on the two opposed surfaces attract one another more and more strongly and accumulate more and more densely, until, as the electrified body approaches very near, a spark is seen to dart across, the two charges thus rushing together to neutralize one another, leaving the induced charge of positive electricity, which was formerly repelled to the other end of the conductor, as a permanent charge after the electrified body has been removed. In Figure 19 is illustrated the operation of gradually lowering down over a table a positively electrified metal ball. The nearer it approaches the table, the more does the electric field surrounding it concentrate itself in the gap between the ball and the tabletop, the latter becoming negatively electrified by influence. Where the electric lines are densest, the tension in the medium is greatest, until when the ball is lowered still further the mechanical resistance of the air can no longer withstand the stress. It breaks down and the layer of air is pierced by a spark. If oil is used as a surrounding medium instead of air, it will be found to stand a much greater stress without being pierced. 24. Attraction due to influence. We are now able to apply the principle of influence to explain why an electrified body should attract things that have not been electrified at all. Figure 18, on page 26, may be taken to represent a light metal ball be hung from a silk thread presented to the end of a rubbed glass rod A. The positive charge on A produces by influence a negative charge on the nearer side of B and an equal positive charge on the far side of B. The nearer half of the ball will therefore be attracted, and the farther half repelled, but the attraction will be stronger than the repulsion, because the attracted charge is nearer than the repelled. IIence on the whole the ball will be attracted. It can easily be observed that if a ball of non-conducting substance, such as wax, be employed, it is not attracted so much as a ball of conducting material. This in itself proves that influence really precedes attraction. Another way of stating the facts is as follows. The tension along the electric field on the right of B will be greater than that on the left, because of the greater concentration of the electric lines on the right. 25. Dielectric power. We have pointed out several times what part the intervening medium plays in these actions at a distance. The air, oil, glass, or other material between does not act simply as a non-conductor. It takes part in the propagation of the electric forces. Hence Faraday, who discovered this fact, termed such materials dielectrics. Had oil, or solid sulfur, or glass been used instead of air, the influence exerted by the presence of the electrified body at the same distance would have been greater. The power of a non-conducting substance to convey the influence of an electrified body across it is called its dielectric power, or was formerly called its specific inductive capacity. See Article 56 and Lesson 23. 26. The Electrophorus. We are now prepared to explain the operation of a simple and ingenious instrument, devised by Volta in 1775, for the purpose of procuring, by the principle of influence, an unlimited number of charges of electricity from one single charge. This instrument is the Electrophorus, Figure 20. It consists of two parts, a round cake of resinous material cast in a metal dish or sole, about 12 inches in diameter, and a round disc of slightly smaller diameter made of metal, or of wood covered with tinfoil, and provided with a glass handle. Shellac, or sealing wax, or a mixture of resin, shellac, and Venice turpentine, may be used to make the cake. A slab of sulfur will also answer, but it is liable to crack. Sheets of hard ebonyized India rubber are excellent. But the surface of this substance requires occasional washing with ammonia and rubbing with paraffin oil, as the sulfur contained in it is liable to oxidize and to attract moisture. To use the electrophorus, the resinous cake must be beaten or rubbed with a warm piece of woolen cloth, or, better still, with fur. The disc or cover is then placed upon the cake, touched momentarily with the finger, then removed by taking it up by the glass handle. When it is found to be powerfully electrified with a positive charge, so much so indeed as to yield a spark when the knuckle is presented to it, the cover may be replaced, touched, and once more removed, and will thus yield any number of sparks, the original charge on the resinous plate meanwhile remaining practically as strong as before. The theory of the electrophorus is very simple, provided the student has clearly grasped the principle of influence explained above. When the resinous cake is first beaten with fur, its surface is negatively electrified, as indicated in Figure 21. When the metal disc is placed down upon it, it rests really only on 3 or 4 points of the surface, and may be regarded as an insulated conductor in the presence of an electrified body. The negative electrification of the cake therefore acts by influence on the metallic disc or cover, the natural electricity in it being displaced downwards, producing a positive charge on the underside, and leaving the upper side negatively electrified. This state of things is shown in Figure 22. If now the cover be touched for an instant with the finger, The negative charge of the upper surface will be neutralized by electricity flowing in from the earth through the hand and body of the experimenter. The attracted positive charge will, however, remain, being bound as it were by its attraction towards the negative charge on the cake. Figure 23 shows the condition of things after the cover has been touched. If, finally, the cover be lifted by its handle, the remaining positive charge will be no longer bound on the lower surface by attraction, but will distribute itself on both sides of the cover, and may be used to give a spark, as already said. It is clear that no part of the original charge has been consumed in the process, which may be repeated as often as desired. As a matter of fact, the charge on the cake slowly dissipates, especially if the air be damp. Hence it is needful sometimes to renew the original charge by afresh beating the cake with the cat's skin. The labor of touching the cover with the finger at each operation may be saved by having a pin of brass or a strip of tinfoil projecting from the metallic sole onto the top of the cake, so that it touches the plate each time, and thus neutralizes the negative charge by allowing electricity to flow in from the earth. The principle of the Electrophorus may then be summed up in the following sentence. A conductor, if touched while under the influence of a charged body, acquires thereby a charge of opposite sign. Since the electricity thus yielded by the Electrophorus is not obtained at the expense of any part of the original charge, it is a matter of some interest to inquire what the source is from which the energy of this apparently unlimited supply is drawn. For it cannot be called into existence without the expenditure of some other form of energy, any more than a steam engine can work without fuel. As a matter of fact, it is found that it is a little harder work to lift up the cover when it is charged than if it were not charged. For, when charged, there is the tension of the electric field to be overcome as well as the force of gravity. Slightly harder work is done at the expense of the muscular energies of the operator, and this is the real origin of the energy stored up in the separate charges. The purely mechanical actions of putting down the disc on the cake, touching it, and lifting it up, can be performed automatically by suitable mechanical arrangements, which render the production of these inductive charges practically continuous. Of such continuous electrophores, the latest is Wimshurst's machine, described in Lesson 5. 27. Free and bound electrification. We have spoken of a charge of electricity on the surface of a conductor, as being bound when it is attracted by the presence of a neighboring charge of the opposite kind. The converse term, free, is sometimes applied to the ordinary state of electricity upon a charged conductor, not in the presence of a charge of an opposite kind. A free charge upon an insulated conductor flows away instantaneously to the earth, if a conducting channel be provided, as will be explained. It is immaterial what point of the conductor be touched. Thus, in the case represented in Figure 17, wherein a plus electrified body induces electrification at the near end, and plus electrification at the far end of an insulated conductor, the charge is bound, being attracted, while the plus charge at the other end, being repelled, is free. And if the insulated conductor be touched by a person standing on the ground, the freed charge will flow away through his body to the earth, or to the walls of the room, while the bound charge will remain, no matter whether he touch the conductor at the far end, or at the near end, or at the middle. 28. Method of charging the gold leaf electroscope by influence. The student will now be prepared to understand the method by which a gold leaf electroscope can be charged with the opposite kind of charge to that of the electrified body used to charge it. In Lesson 2, it was assumed that the way to charge an electroscope was to place the excited body in contact with the knob, and thus permit, as it were, a small portion of the charge to flow into the gold leaves. A rod of glass rubbed on silk being plus would thus obviously impart plus electrification to the gold leaves. Suppose, however, the rubbed glass rod to be held a few inches above the knob of the electroscope, as is indeed shown in Figure 12. Even at this distance the gold leaves diverge, and the effect is due to influence. The gold leaves, and the brass wire and knob, form one continuous conductor, insulated from the ground by the glass jar. The presence of the plus charge of the glass acts inductively on this insulated conductor, inducing electrification on the near end or knob, and inducing plus at the far end, i.e. on the gold leaves, which diverge. Of these two induced charges, the minus on the knob is bound, while the plus on the leaves is free. If now, while the excited rod is still held above the electroscope, the knob be touched by a person standing on the ground, one of these two induced charges flows to the ground, namely, the free charge, not that on the knob itself, for it was bound, but that on the gold leaves which was free, and the gold leaves instantly drop down straight. There now remains only the minus charge on the knob, bound, so long as the plus charge of the glass rod is near to attract it. But if, finally, the glass rod be taken right away, the charge is no longer bound on the knob, but is free to flow into the leaves, which once more diverge, but this time with a negative electrification. 29. The return shock. It is sometimes noticed that, when a charged conductor is suddenly discharged, a discharge is felt by persons standing near, or may even affect electroscopes, or yield sparks. This action, known as the return shock, is due to influence. For in the presence of a charged conductor, a charge of opposite sign will be induced in neighboring bodies. And on the discharge of the conductor, these neighboring bodies may also suddenly discharge their induced charge into the earth, or into other conducting bodies. A return shock is sometimes felt by persons standing on the ground at the moment when a flash of lightning has struck an object some distance away.